Hello, stat students, back at you here with the third and final sampling distribution lesson. The first lesson of this unit talked about the idea of why we have sampling distributions and their ability to get to a normal shape for us from a skewed distribution, and talked about wanting low bias with a random sample, low variability with a big sample size, and a little bit about the notion of the central limit theorem, which we then followed up on just talking about the mean side of this. So the mu of the x bars being mu, and the sigma of the x bars being sigma over root n on the mean side. So that was again in lesson 2 with mean amount of money, mean score, mean distance, things like that. And we're going to end here in lesson 3 with proportion. So this would be all situations where we're just trying to calculate a proportion of people who agree with something, who like something, the proportion of students who passed, the proportion of people who live in a certain area, whatever it happens to be. So jumping in here, what you're going to want to know here is how to describe a sampling distribution of proportions, okay? How to evaluate the conditions or the rules of thumb here for these, which are similar to the means, and to be able to calculate probabilities with these here. So first of all, similar ideas around variability and shape. So you can see here in this example, this is a distribution that started out skewed to the right, but as the sample size increased, now all of a sudden we got this normal curve, or the sampling distribution, which has a lower standard deviation because of the increased sample size. And we get to a point where, yes, it's still a little skewed to the right there, as you can see that the mean, median, and mode are not all the same. But we're getting it closer and we're making it skinnier, that standard deviation going from 1 to 0.25. Here in this example, you're just seeing a distribution that was already normal, which is the shaded in kind of orange distribution there, or red, or whatever that is. And then you're seeing what happens when we increase the sample size. Okay, so again, what that means is this original distribution is one individual at a time. And then this distribution here is 4 individuals at a time. So it might be what percent of people like having an open hour, and all of a sudden that gets to be closer to the same percentage. And then it gets to be closer yet when you get to n equals 16. And then finally, the tall and real skinny one there is an n equals 64, which is just getting at the idea that as n increases, variability decreases. Now, keep in mind, it's variability that decreases. It's not that as n increases, bias decreases. Okay, this is not necessarily the case because bias, again, is all around the idea of random sampling rather than sample size. So doesn't matter how big your sample is. If it's not random, it's still a problem. If it is random, then you eliminate or alleviate that bias. So in describing a sampling distribution with proportions, last lesson, sorry, we had mu of the x bars equals mu, which is the mean side of this, okay? Now we have mu of the p hats equals p. So you can see the x bar gets replaced with the p hat, which is just the sample proportion instead of the sample mean. The mu gets replaced by the p, which is the population proportion instead of the population mean. And then similarly, and this is a new formula now, we have the sigma of the p hat. So last lesson we had sigma of the x bars was sigma over root n. This one you can tell is a little more complicated formula. But again, one that's on our formula sheet. It's not one you need to memorize, but the notation is important here. So the sigma of the p hats, which means the spread of a bunch of p hats. If I asked 1,000,000 samples of 50 people, do you like having an open hour? I would graph all of these p hats, and it might be centered at something like, I don't know, maybe 80% of students like having an open hour. And I would get all these p hats that in one sample I got 80%, and the next one I got 79, and the next one I got 81, and so on. So I've gotten all these p hats, which again is the sample proportion from a bunch of different samples, okay? And I'm just graphing all of those p hats, and I wouldn't do that because I'm not going to graph 1,000,000 p hats, but a computer would. or our knowledge helps out with this as well and over time. But the idea is this is a sampling distribution of p-hats. So this standard deviation of the p-hats is how much those p-hats would be spread out, rather than just how much a p would be spread out. All right. The idea of knowing that the shape is going to be normal, okay? So the previous slide was the center and spread again, which was mu of the p-hats equals p, that's the center. Sigma of the p-hats equaling the square root of p times 1 minus p over n, that's the spread. Now the shape is a little different. So for the last lesson, this whole idea with shape was that n was 30 or more. And that was for means. That's the mu of the x bars. Now here, and I apologize it got cut off, but what we're looking at here is n times 1 minus p and n times p both have to be 10 or more. Okay, and what that is really saying is the n times p is referring to the successes. Whatever we're talking about, whatever a success is in that situation, it could be somebody liking open hour. It could be somebody successfully robbing a bank, sadly. But that idea of n times p is whatever we define as a success. This is going to tell us how many successes would we have. So in other words, if the Twins won 75% of their games and they played 40 games, then they would win 40 times 0.75 or 30 games, which of course is 10 or more. If they won 75, then here's the fails down here, which means if they played 40 games, but they lost 25% of them, so 40 times 0.25 would be 10, which of course is greater than or equal to 10. So as you can see here, if the Twins had a 75% success rate, that means they have a 25% fail rate. We would need to take a sample size of at least 40 to make that work. Because if we only took 39, this number here would not be 10 or more, and that would be a problem. That would mean that we have not fulfilled our requirement to ensure the central limit theorem, which again is what all of this is based around. Did we take a big enough sample size for the central limit theorem to ensure normality? And if we wouldn't have taken 40 here, it wouldn't have been a big enough sample size. Now, the important thing to note is as this number changes, this 0.75 value, that n is going to change. So if it's 50-50, then it only takes a sample of size 20 because 50% of 20 is 10 and 50% on the fails times 20 is also 10. But if it's 99%, then that becomes a lot different because that means we fail 1% of the time. So we would need n to be a lot bigger in order for n times 0.01 to equal 10 or more. So if we look at this in an example here, this here we have 48% of a voting population supports a candidate for office. So that means this 48% is P. That's considered the population percentage. So in this case, P equals 0.48. And it asks to describe the sampling distribution of P hats for random samples of 384 voters. So what we have here is we are saying that we think if we take and poll 384 voters at a time over and over and over and over and over again, that we are going to get a bunch of P hats, and they won't always be 48%. Some polls will return 49%, some 47%, and so on. But now this is asking us to describe that sampling distribution. Again, when you see describe the sampling distribution, center, shape, spread. Okay, it doesn't matter what order, but you need to include all three of those when you are describing a sampling distribution, and you need to make sure to include notation. So before I even put any values in, from my formula sheet, I already know that my center is mu of the p hats, which equals p, and my spread is sigma of the p hats, which equals the square root of p times 1 minus p over n. So in this situation, we've already known or been told here, and you would be told every time in this situation, that P is 0.48 in this particular example. So this would be 0.48 or 48%. You don't have to write both, but you should write one or the other there. The spread would be 0.48 times 1 minus 0.48 over n, and again it told us n in the question, which is 384. So we calculate that, 0.48 times 0.52 divided by 384, all square rooted under the radical, which is approximately 0.0255. What that means is this distribution that we have up here is going to be centered at 48 with a standard deviation of about 2.5%. So one standard deviation away will be down here at about 45.5. That would be the P minus 1 sigma. And then up to 2.5%, so that would be up at 50.5, would be the, and you won't have to do this, I'm just showing it to you here, would be P plus 1 sigma. And so my drawing is a little off. It's a little further out than 1 standard deviation away based on how I drew my curve, but that's our center and spread. So center, check. Spread, check. And again, you could write that as 2.55% if you want. Now the shape, again, comes back to that n times p and n times 1 minus p. Are those both 10 or more? And so when we look at this here, 384 times 0.48 and 384 times 1 minus 0.48. Okay, so in each one of those cases, 384 times 0.48 is about 184.32. It doesn't really matter the 0.32 there actually, because we're already over 10. And this is 199.68. So what we're really saying here is, in a sample of 384 voters, we'd expect about 184 of the voters to vote for this candidate and about 200 people to not vote for this candidate. But either way, these are both 10 or more, which is all that really mattered for us right now. And I ran out of space here, but what we would say then is, since both are 10 or more, central limit theorem ensures roughly normal. Again, don't say normal, but roughly normal. Okay. Again, apologize for how that's disorganized, but since both, and you could get specific here, n times p and n times 1 minus p are both 10 or more, the central limit theorem ensures a roughly normal sampling distribution, which just means that that graph will be roughly normal. So that is our center, shape, and spread. And that's what you would do if you're asked to describe a sampling distribution. This is often part A on a sampling distribution question. Now, the other part of this example would be something like this. In the same sort of scenario with P equaling 0.48 and N equaling 384, what is the probability that a majority of voters would support the candidate? Which of course would be something that we'd be very interested in here, is the idea of what are the chances we get over 50%. So this question in a probability statement is asking, what's the probability that a p hat, a sample proportion, would be greater than 50%? And similar to what we did last unit and similar to what we did last lesson, we would go down here and we would calculate that z. So in this case, that's p hat, which is the statistic, minus p, which is the population parameter. This is also mu of the p hats, okay? All over the sigma of the p hats, which looks like this, and we calculate. Okay, so again, in all of these cases, this is statistic minus parameter over standard error, really, which is the sampling distribution, standard deviation, if you will. We would call standard error because we're going to bring in n, and it's not just sigma alone. So here, the p hat is 0.50, the p is 0.48. We actually calculated this denominator on the last one. It was 0.0255, but I'll just write it here. 1 minus 0.48 all over 384. So what we end up getting here is a z-score of about 0.78. So what we're calculating here is what's the probability that our z-score is greater than 0.78. Again, this here is simply that we have converted this from the graph that's centered at 48% to the graph that's centered at 0 standard deviations. Okay, so -1, we already figured out was about 2.5% standard, was a standard deviation. So this is about 0.455, and 1 is at about 0.505. Okay, so this is just a conversion of the original percentages, the p-hats and the p's, to the z-scores here. And so it's just, again, like centimeters to inches or something like that. We are converting the specifics of this problem to the general idea of what's the z-score, which is just how many standard deviations are we from the mean. So because the standard deviation here was about 2.5%, not surprisingly, we found that to get a 2% above the P, which is the 50 is 2% above 48, that's a little under 1 standard deviation above the mean because it's not quite 2.5% above the mean. So now we get our calculation from this, and this again is the second VARS normal CDF, and we here are at 0.78. Here, I'll draw it up on this. So we're about right here, which is at 50% or 0.78 for a z-score. And we want the chances that we could get more than that, so greater than that. So we are looking for that area right there. So we go to second VARS, we go to our normal CDF. Our lower bound here is 0.78. Our upper bound is 99, or some big number. Okay, and that ends up giving us an answer of about 0.2177. Now, that's our final answer. The probability that we get a z-score above 0.78 is 0.2177, or 21.77%. So a little under a quarter of the time, we can expect to get over 50% of the vote. Now, again, for what work you should show here is you should show at least one of these two probability statements. Okay, you should show the calculation of the z here, down here. Sorry, I don't mean to just point at that, the whole thing here, calculation of the z, and then of course you have your final answer. You would not necessarily need to draw the picture here, but that's just what's going on in this particular problem. But there's a 21.77% chance that a sample would yield a greater than 50% of people voting for this candidate. Again, the question says greater than, so we'll just leave it like that by saying a majority of the voters. It doesn't matter. If you would have done greater than or equal to, it wouldn't have changed your answer here. Finally, just some things to consider if we get a really small p-value, so meaning our final answer, and I know that's confusing because we call p the population proportion, but our answer, so on this last question, 0.2177 was the p-value, which is a probability value. If that ends up being really small, so let's say we have a normal curve, and we get, let's say it was 48% was the center, and we got 70% of the vote. So we were way out here. Okay, even further than that, most certainly, but I'm just going to put it there for now. What are the chances that a sample would return over 70% of the vote for this candidate? Well, that would be crazy to find because we only expect this candidate to get about 48% of the vote. So what could happen there? One, we could have not selected a random sample. Perhaps we went around to a certain political, a heavy Democrat or Republican area and asked who they're going to vote for. And it turned out that 70% of them were going to vote for this certain candidate. Well, that's not a random sample because that's not a true cross-section of voters. So that could have been one thing. Now, a second thing is the 48% could have been wrong to begin with. Maybe this candidate is going to receive more like 70% of the vote, and we were just flat out wrong with 48%. So that's a second possibility. The third and least likely is we just got a really rare sample. It just somehow worked out super weird this time, which it never would be like this that we saw here with 384 voters. That would be a 1 in quintillion possibility. but we end up typically working between the first two. And what we're doing is a lot of times we say, well, let's just pretend we took a random sample, so then 2 would be the issue. But the other side of it is, what if we know for certain that it's 48%? Then the random sample was probably the issue. And you will have questions where this goes both ways, but we'll get very particular about those questions and talk a lot more about them. Um, but that's something to consider when you get a really small p-value, a really small final answer, again, different than the population parameter here, which was 48. The p-value is your final answer from our probability question there. If it's really small, then you want to start to consider these 3 areas, and particularly the top 2. We'll talk more about that as a group, but thank you very much for listening and watching. As always, if this leads to any questions, please make sure you ask.